Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, machine learning, optimization, signal processing, etc. This is the second part of the tutorial on the extended Kalman filtering. In the first part of the tutorial we thoroughly explained how to derive the extended Kalman filter from scratch. In this second part of the tutorial, we explain how to implement the extended Kalman filter in Python from scratch. To make the long story short, in this video tutorial, we explain how to write a Python class that implements the extended Kalman filter. The class is given over here. Then, we explain how to test this class on a simple example of a nonlinear system. To test the implementation of the extended Kalman filter and this class, we will derive a nonlinear state space model of a pendulum. Then, we will compute Jacobian matrices of this state space model, and I will explain you how to implement these Jacobian matrices in Python. By the end of this video, you will be able to generate these nice graphs that show the convergence of the extended Kalman filter. But before I start, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as all the video tutorials posted on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. Before watching this video tutorial, it's a very good idea that you go over and that you study the first part of the tutorial. You can find the first part of the tutorial by clicking over here and by reading this webpage. In the first part of the tutorial, I explain thoroughly how to derive the extended Kalman filter. Under the assumption that you know how to derive the extended Kalman filter and that you know the basic equations of the extended Kalman filter, I will proceed. One additional comment before I start. The GitHub page with all the codes that I will present in this video tutorial is given over here. You can find this GitHub page by clicking over here. And in addition, this webpage tutorial is also given in the description below this video tutorial. To test the performance of the extended Kalman filter, we need to consider a test example. In this video tutorial, we consider a pendulum system. Pendulum system is a classical dynamical system, and we can say that this system is actually a hello world example of control engineering, because you usually test all the control methods by using a relatively simple example, and arguably the most simplest example of a nonlinear system is a pendulum. So what is a pendulum? You can read more about a pendulum by clicking over here and by reading this tutorial that I created. Pendulum is nothing less than a mass, m, attached to the ceiling by using a rod. We assume that the rod is massless, and we assume that the length of the rod is L. Theta is the angle of the rod with respect to the vertical direction. The state space model of the pendulum is given over here. x2 is the angular velocity and x1 is the angle theta. Now, to develop a Kalman filter for this system, we need to make a few assumptions. The first assumption is about our measurement equation. Here, we assume that we can only measure the angle theta of the pendulum. That is, we can only measure this angle. And the goal of the extended Kalman filter is to reconstruct the complete state of the system, that is, the angle theta and theta dot, that is x1 and x2, from the measurements of theta. Our state space model, given by the equation number 1, is in the continuous time form. Although we can develop the extended Kalman filter by directly using the continuous time form, we are not going to do that. We are not going to do that because the first part of this tutorial is based on the discrete time system model. Consequently, in order to keep the second part of the tutorial consistent with the first one, we need to discretize this system. To discretize the system, first we will write our original state space model in this compact form, where beta is the function given by the equation number 4. We use the forward Euler discretization method to approximate the first derivative and to discretize our state space model. We can simply approximate the first derivative by using finite differences. So x dot is approximately equal xk minus 1 divided by delta t. And here k is a discrete time instant and delta t is the discretization step size. And the left part should be equal to our function beta at x at the time instant k minus 1. From the equation number 5, we obtain the equation number 6. Then, by replacing the approximate symbol over here with the equality sign, we obtain the equation number 7. And the equation number 7 is a discrete time equivalent of our continuous time system. Next, we can combine the expression for the function beta that is defined in the equation number 4 with the equation number 7 to arrive at the equation number 8. And this equation can be written in this form given by the equation 9, where the function f is given over here. Here it's very important to stress that this function does not depend on time, and consequently we don't have the discrete time k minus 1 in the subscript of the function f. By using the notation from the first part of this tutorial, we can write the output equation corresponding to our state space model as follows, where the output equation is simply saying that we are measuring the x1 component of our state space vector. The first step that you need to perform when applying or when developing the extended Kalman filter is to compute the Jacobian matrices of the function f, that's basically a discrete time state space equation, and the Jacobian matrix of the output equation. So let's start with the Jacobian matrix of our function f. To compute the Jacobian matrix of f, we first need to partition the matrix f. We are basically saying that this vector function f has the component f1 and f2, where f1 is given by this equation, f2 is given by this equation. Next, we need to compute the Jacobian matrix of this vector function. The Jacobian matrix is defined as follows. We take the first equation, or actually the first part, f1, and we compute the derivative with respect to x1 k minus 1. Then we take the same function and compute the derivative with respect to x2 at k minus 1. We repeat this procedure for f2, and we construct the second row of our Jacobian. And if we compute the partial derivatives of these two equations, f1 and f2, we obtain our Jacobian matrix. The Jacobian matrix of the output equation is defined in the similar manner. We take the function g and we compute the partial derivatives with respect to x1k and x2k. And since we are only measuring x1k, this will be our Jacobian. This is basically a C matrix. On the basis of the calculated Jacobians, we obtain the following matrices necessary for the extended Kalman filter. We obtain the matrix ak-1 by evaluating Jacobian at this state. This is actually the a posteriori state computed at the time instant k-1. And if we substitute this state, we obtain this matrix ak-1. On the other hand, since the Jacobian of the output function is a constant, the ck matrix will be constant. So these two matrices, ak-1 and ck, are very important for the implementation of the extended Kalman filter. In the sequel, we explain how to implement the extended Kalman filter in Python. For that purpose, I will briefly revise the main equations of the extended Kalman filter from the first tutorial. The extended Kalman filter consists of two steps. In the first step, given by the equation number 20, we start with a posteriori estimate, denoted like this, and we update this estimate by propagating it through dynamics to compute the a priori estimate for the time step k. We do the same thing for the covariance matrix. This is the a posteriori covariance matrix for the time step k-1, and we propagate this covariance matrix by using this equation in time to compute the a priori covariance matrix for the time instant k. Then, in the step number 2, we collect the measurement, we compute the Kalman filter gain, given by the equation number 22, and then we compute the a posteriori state estimate by using the measurement and some additional information. And finally, we update the a priori covariance matrix to compute the a posteriori covariance matrix. And we need to repeat these two steps. However, we need to initialize our Kalman filter. And we do that by selecting or by guessing an initial estimate x0 and the covariance matrix p0. Some might say that it's very easy to implement these two steps, and my answer is you're wrong. It's actually very challenging to write a disciplined code that can be easily debugged that implements the extended Kalman filter, and that's the whole purpose of this video tutorial. Here's my attempt to create a disciplined Python implementation of the extended Kalman filter class. First, I need to initialize my Kalman filter. I do that over here in this function init by specifying x0. x0 is the initial guess of the state vector. Then, with p0, p0 is the initial guess of the covariance matrix. With q and r, q is the covariance matrix of the process noise, and r is the covariance matrix of the measurement noise. And finally, dt is the discretization period for the forward Euler method. Over here, I initialize these variables, then I define my gravitational acceleration constant and length of the pendulum. Know that these are the parameters of my pendulum state space model. Then I initialize this variable current time step to 0. This variable corresponds to k, that is, to the discrete time instant. Then I initialize a list over here. This list will store the a posteriori state estimates. And notice over here that I immediately append this list with x0. To help you to better understand this video tutorial, I will write next to these lists the variables that they store. This list will store xk-1 plus hat. Similarly, I need to initialize a list that will store the a priori state estimates. That is, this list will store xk minus hat. Then I need to initialize and to define lists that will store the covariance matrices. This list over here will store p k-1 plus. That is, it will store the a posteriori covariance matrix. The list initialized over here will store the a priori covariance matrix denoted like this. This list will store the Kalman gain matrices k with an index k, and this list over here will store the errors. The errors are simply yk, that that is my output, minus the output prediction evaluated at xk minus hat. This term is also called the innovation. That was our init function. The next step is to define a function that actually evaluates a continuous time state space model. That is, we need to define a function that will evaluate this model. And consequently, here's the function. This function takes x and t, state and time, as an argument, and it returns the right-hand side of our state equation. Next, we need to define the discrete time dynamics. That is, we need to define this state equation in discrete time. Here's the definition. It takes a discrete state and it computes the right-hand side of this equation. Next, we need to define the Jacobian matrix of the state equation. That is, we need to implement this matrix over here. The function given over here returns the Jacobian matrix evaluated at the discrete state xk. The next step is to define the Jacobian matrix of the output equation. That is, we need to define this Jacobian matrix. Here's how we do that. This function returns our C matrix. Finally, this function returns the output equation value at the state xk. That is, it simply returns x1, since this is our output equation. Let's proceed. Next, we need to implement these two equations. The first equation will propagate this a posteriori state estimate in time through our dynamics. And the second equation will propagate the a posteriori covariance matrix in time to compute this a priori covariance matrix. So let's do that. Here's the function. Over here, xk minus 1 is actually the a priori state estimate for the time instant k. That is, xk minus is our xk minus hat. To compute this value, we need to call our discrete time dynamics, and we specify this value over here. This list value corresponds to xk minus 1 plus hat. Here we propagate the state. Similarly, over here, we propagate the covariance matrix. This variable over here is our pk minus, and the value of this list, that is the entry of this list, is our pk minus 1 plus. After we perform these two steps, we simply append this value to the list, and we append this value to the appropriate list that stores the covariance matrices, and we update our time step. That is, k becomes k plus 1, or k minus 1 becomes k. Next, we need to implement the second step of the extended Kalman filter. First, we need to compute the Kalman gain, kk. Then we need to update the a priori estimate to compute the a posteriori estimate. And finally, we need to update the a priori covariance matrix to compute the a posteriori covariance matrix. So let's do that. First, we need to extract our CK matrix. We do that by calling this function. Then, over here, we need to compute the KK matrix. And here's how we do that. First, we compute the S matrix, and S matrix is this part over here without inverse. Then, over here, we simply implement this equation, and I will expand this so you can clearly see what's happening over here. It's pretty much straightforward. Finally, we need to compute our estimate. That is, we need to implement this part over here, and here's the implementation. And after that, we need to compute the a posteriori covariance matrix. That is, we need to compute this part over here, and we do it over here. Finally, we need to update the lists that store the vectors and matrices. We update the list that stores the KK, we update the list that stores the errors, we update the list that stores the a posteriori estimates, and we update the list that stores the a priori, and better to say a posteriori covariance matrix. That was the class implementing the extended Kalman filter. We need to save this class in the specific folder, for example over here, and make sure that if you're using the Spider environment that the current folder in which you save this file is active. Next, let's explain how to use this class. The first step is to import the required libraries. First, we import the NumPy library, then we import the library for plotting, then from scipy.integrate we import ODE_int. This function is used to integrate the continuous time dynamics of our pendulum, and then finally from our file extended Kalman filter we import our class over here. Next, we select the discretization time step for the forward Euler method. We set the initial condition for generating the simulation data, and over here I will stop for a second and explain you the general idea. Our idea is to simulate the continuous time dynamics given by this equation, and by simulating this dynamics by using the built-in Python solver in this function ODE_int, we will generate our true data. And we will feed this data, that is, we will feed the theta angle computed from this data into our Kalman filter. Consequently, over here I need to define my continuous time dynamics. That is, I need to define this function. Here's how we do that. We specify state and time, we specify the parameters, and we specify the right-hand side of our equations. To generate the data, I need to specify the initial condition. I need to specify the time steps for simulations. We will consider 400 time steps. Then I need to generate the total simulation time vector. I start from 0. This will be the end time, and this will be the delta time that's equal to 0.01. Over here, I integrate the dynamics. So let's do that. But before I do that, I will erase this part over here, and I will clear my workspace. Perfect. Let's see the dynamics. Okay, over here is our dynamics. Here it is. And you can uncomment this part over here to see how our dynamics looks like. Here's our dynamics. x1 is the angle theta, and x2 is the first derivative of theta, that's the angular velocity. I will keep this part commented since I don't want to destroy other graphs in this video tutorial. The next step is to compare the forward Euler discretization with the discretization performed by this function ODE_int. This is very important for understanding the model uncertainties and how accurately our discrete time model can represent the true or continuous time dynamics. For that purpose, I need to define the forward Euler state. Here it is. Then I need to define the initial values. The initial values for the simulation will be equal to the initial state for the continuous time dynamics, and over here I propagate the forward Euler dynamics. That is, I simply propagate this equation in time starting from some x1 0 and x2 0. And let's see what will happen after I propagate these dynamics. Here it is, here are the results. And in this tutorial I can show these results on a larger screen and using a slightly better resolution. So here's the angle x1, that is theta, computed by using the ODE int method, that's the red line. And the red line represents the true dynamics, that is the true angle theta. And the blue line represents the discretization of our dynamics, that is the discretized theta by using the forward Euler method. We can see that the forward Euler method can relatively accurately, under quotes relatively of course, represent the continuous time dynamics. And that's fine. We know that we are creating some errors, however we can create or we can also quantify these errors. Next, we create the Kalman filter object. First, we need to specify the initial guess of our states. I take the true state that's used for generating the data and I perturb it by a random value. I sample from a Gaussian normal distribution and I multiply the value by 4. Then I specify the initial value of the covariance matrix, it's equal to P0. Then I specify my dt, the dt is equal to delta time for the simulation of the continuous time dynamics. I specify the Q matrix, that is the matrix that defines the process noise. I don't have a process noise, consequently I will assume a very small value of Q. And since I don't have a measurement noise, I will assume a very small value of R. Over here, I create the extended Kalman filter. I use initial guess, P0, Q, R, and dt. So let's do that. Cool. Here is our extended Kalman filter. It's being created. And in this for loop, I will simulate the extended Kalman filter. We have two steps. In the first step, I propagate the a posteriori estimate and a posteriori covariance matrix. That is, I call this function propagate dynamics. The propagate dynamics is defined over here. Next, once I do that, I call the second function compute the a posteriori estimate and I specify my measurement. Here I take theta or x1 from the simulation of my continuous dynamics. Let's run our Kalman filter. I will select this part and I will evaluate this part over here. And in a fraction of a second we obtain the result. The next step is to extract the estimates. I do that by simply going over this for loop. I extract this variable given over here, estimates a posteriori, and you can simply select this part to see these estimates. Here they are. I want to extract x1, x2, and I want to compare these values, that is these estimates, with the true state values. Over here I extract the estimates, and over here I compare these estimates with the true values. So let's do that and let's analyze the results. And here are the results. These graphs are also given over here, and it's easier to explain them on this bigger screen. What happens over here? We start with some initial estimate of the angle theta. We start from here. The true angle behaves as a red line in time. We can see that the filter quickly, that is in maybe one or two steps converges approximately to our true angle. That's very good. This shows that our filter is working. And let's see what happens with velocity. Here assume some initial value of the velocity, and you can see that the filter also converged to the true value of the velocity. However, the convergence is a little bit slower. This is because we are not directly measuring the velocity. All these codes are posted on my GitHub page. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.